Course 19 CSE 212 Data Structures and Algorithms. So today's topic is asymptotic analysis. So last two lectures we saw about the importance of data structure, then we saw what is ADT, right? So now during the discussion of those topics, we were talking about the efficiency part of when you choose a good data structure, you can design an efficient algorithm, right? So now we need to measure efficiency of your algorithm. So asymptotic analysis is a tool which helps you to measure the efficiency of your algorithm. Okay, so let's see what is asymptotic analysis. So analysis of algorithms is very much important, right? So only if you get the response faster, you will like it, right? Anything, let it be anything, you will be more giving importance to quick response, right? So you will not wait for so long to get some response. Same way in algorithms also, in computers, we are we are expecting a very fast response, okay, which consumes very less space also. So as I told earlier in my previous videos, like time complexity and space complexity, or time and the space are the two parameters that we use to measure the efficiency of algorithm. Okay, so another parameter which helps you to find the efficiency or compute the time complexity of the algorithm is the input size. Okay, the input that you give into the algorithm, based on that your efficiency or the response time may change. Okay, so here are the few examples of running time. We normally call it using a function of n, where n is a number of, or n is a size of the input. Okay, so n square, n log n, etc. are few functions. So we will see in detail how you will be doing this asymptotic analysis. So one of the method that we are going to use here is counting primitives. Okay, so based on the number of times or number of evaluations that you are doing, right? So based on that you are computing the efficiency. Okay, so normally primitive operations will tell that they will be taking constant amount of time. Then it depends only on the frequency count, that is how many times that particular statement is executed. So based on that the time complexity will be computed. Okay, so now we'll be given with a pseudocode. I'll tell you this finding the time complexity is not an experimental setup, it is a theoretical analysis. Okay, experimental setup in the sense, like you will start a stopwatch, right? And then you will tell when you get the response first, you will stop it. So you measure the time, actual time taken for you to see the result, right? So it is not experimental setup. Why? Because each algorithm, even if the same algorithm is executed in different machines, the time that your stopwatch will giving you will be different. Because say I have two machines, one is a very high end machine and another one is very low end. I am giving the same algorithm to both the machine, right? So you will be getting the results at different times. Again, the next thing is like if the same machine is loaded with a lot of other works also, again some CPU cycles will be consumed by that. So experimental setup is not a good measure in the case of this theoretical in the case of this efficiency analysis. Okay, so that's why we are going to do an theoretical analysis that we call it as asymptotic analysis. So we have different asymptotic notations that we'll see in the upcoming slides. Okay, so here we can see few examples of a primitive operation, right? Evaluating an expression, okay, is one of the primitive operation which you are not defining. It depends on the time taken by the architecture, right? You can't decide the how much time you are going to take on that evaluation. It's not in your hand. It is depends on the architecture that you have. So we assume that that is constant. Okay, how many ever time you do in that machine, it is going to take that much time only, right? So that part is assumed as constant. So evaluating an expression, assigning a value to a variable, indexing into an array, calling a method, returning from a method, all of these statements are called as primitive operations. Okay, so these primitive operations are actually part of your code. So this primitive operations take constant amount of time, but how is it varying is how many times this primitive operations are invoked, right? So based on the frequency and the number of times this expression is used, based on that you are finding the time complexity of a single statement in the program or in the algorithm. Okay, so the same thing here, given two or more algorithms to solve the same problem. Okay, so you have multiple ways to solve a problem, right? You have two or more algorithms which helps you to solve the same problem. Now I need a best one, right? So I have to compare which one is best, right? So based on that I will decide, okay, I will select this algorithm for the execution. So how will you decide, or how will you decide or how will you select this algorithm is best, right? So there should be some criteria which helps you to select the algorithm which is best. So okay, so here you can see few criteria. Is it easy to implement or understand or modify, right? How long does it take to run it to completion? How much of computer memory does it use, right? So now we are interested in the last two, that is second and the third criteria, that is the time complexity and the space complexity. So any algorithm, you have an input and the input is transformed into output, right? So you have, see here in this example you can see an input array is feed into sorting algorithm and you get the sorted output, right? So now you are making you are actually going into each elements for doing a sorting, right? So it basically depends on the size of the input that you have in that array, right? What is the size of that array that you are going to deal for the sorting, right? So the running time of an algorithm typically grows with the input size. So now here you have four elements. So any sorting algorithm that you will take, it has to check all the elements in the array, compare it with the all the remaining elements and decide is it a sorted order or it is not a sorted order. So definitely it sorting algorithms complexity here depends on the size of the input, right? So you have if you have say 20, then you have to check all the 20 elements for its correct position. Only then you can declare, okay, I have completed the sorting. So basically now I'll understand that the running time of a program or an algorithm depends on input size. Okay, so this is an important parameter which we are going to use for computing the time complexity of any algorithm. Okay, that is the input size. Now see this example, even on input size. Okay, now I am ready. Okay, I agree that input size is very much important, because as and when the size of the input changes, I am going to invest more amount of time. Okay, so I agreed that. Now think of this situation, even on inputs of the same size. Okay, assume that the input is on the same size, then also running time can be different. So it also depends on the nature of the input. Okay, say for example, in case of say insertion sort. In case of insertion sort, what happens? You will have a nested loop, right? So if I give an input in the sorted order itself, the inner loop will always give a failing condition and you will not execute that, right? So even if the size is same, but the nature of the input is also very much important to define the or to compute the time complexity. Okay, so say here the example is algorithm that finds the first prime number in an array. okay, by scanning it from left to right. So what happens if what is the best case here? Best case is when I am getting my that fastest response, the first response, how fast I can get my response. Okay, so that is the best case. Assume that the first number that you have in the array is 5. Okay, say array is A, so A of 0 contains 5. So what happens? You computed, you wrote the logic for, you wrote the logic for checking the prime number. Okay, and 5 is a prime number. So what happens? Now you are exiting from the algorithm, right? Because your program is asking just to send me the first prime number. Okay, so 5, the first element in the array itself, is a prime number, so it will return. Okay, it will not check the remaining element. Okay, so the best case is where when the condition, that is first prime number, is at the first location of the array. Okay, so what could be the worst case? Worst case is if I have a prime number which is only present at the only one prime number, and that is present at the end. Okay, mind you, the size of the input is same. Okay, so in the case 1, that is case 1 is here, the prime number is in the first location. Okay, so the array size is 10. Okay, so in the array size of 10, the first location is having prime number, so it will take first checking itself will send you the result at first A of 0 contains the first prime number. Okay, now the second case is where you have the element, you have the first prime number, that is only one prime number that is present at A of 9. Okay, so I told you the size is same, so you have 10 numbers in 10 size of the array is also 10 in the second case. So what happens? So 9 A of 9, so I have to check all the 9 elements before, and then I will check the 10th element. So in the both the case, the size of the input is same, but the nature of the input which was in that particular size of array is differing. So it not only depends on the size of the input, it also depends on the arrangement or the nature of the input that you are having in your hand. Okay, so that is why here you can see best case, worst case, average case. So average cases, you can tell any random position in the array, right? So you can't tell, so you will be assigning some probability, what is the probability to have in this each cell in the array, so that you will take an average, and that becomes an average case. So normally we will be talking about the best case and worst case as far as data structures and algorithms course is concerned. Okay, yeah. So now let us take an example of finding the maximum element of an array. Okay, so the algorithm name is array max, and the input to the algorithm is array A, and n is the number of element in the array. Okay, so initially the first step is what? The first element in the array is assigned to a variable called current max. Okay, so this arrow means you are assigning the value of a of 0 to current max. Then you are running a loop. Okay, running a loop and inside the loop you are repeatedly comparing the current max, each element in the array with the current max. If this condition, that is the element that I am considering in array, is greater than current max, then I reassign the value of current max and return current max. Okay, so this is the algorithm for finding the maximum element of an array. Now let us see the time complexity. So as I told, we have to compute the time complexity, that is a theoretical analysis that you are doing. So for that we are going to have counting the primitive operations. Okay, so in the first line, so each line by line you will be finding the number of primitive operation. Say for example in line number 1, that is current max is assigned with a of 0. So you have an indexing operator and an assignment, right? So this are the two primitive operations in this line. Okay, so you have counted, so it becomes 2. Now in the second line, it is a for loop. Okay, so as you all know, for loop contains three parts: initialization, then condition checking, and the updation. Okay, it can be incrementation or decrementation. So here initialization, I equal to 1. So this is your initialization part. So initialization part, as you know, all know, for loops initialization part, it will be executing only one times. So initialization here is the assignment operation, so 1. Then you have a condition checking, right? Condition checking is I less than n. Okay, and you will be having I less than n is one comparison, so you will have one comparison there. Then you have here I equal to I plus 1, that is you have two operations there. Okay, one is arithmetic operation which adds I value by 1, and that added value is assigned to that. So in this second line itself, there are three operations or three statements: initialization, condition checking, and the updation and decrementation, updation. So initialization is done for one time, then comparison is having uh, one primitive operation, that is I less than n. Then you have I equal to I plus 1, that is your incrementation step, so which contains two primitive operations. One is arithmetic operation and the assignment. Okay, so so this condition checking and what you call updation statement, it is running for more than one time, right? That particular primitive operations are executed for more than one time, so you have to find the frequency of that operation. Okay, frequency count of that operation, and you will be multiplying that primitive operation count into number of times that that statement is executed, right? So here in the next line, that is the if decision making this thing, so you have one indexing operator and one comparison. So you have here also two primitive operation, and if the decision is true or if the condition is true, you will be doing this reassignment of current max, so which again has one primitive operation, one indexing operation, and an assignment. So here also 2, and this is return is one primitive operation, so it is going to take one constant time 1. Okay, so of which this is the first line is not part of the repetition, so this line is going to have the time complexity of 2 only, because there are only two primitive operations done. But whereas this for loop, you have to find the frequency of each statement, how many times it is executed, and this return current max will be executed only once, so this is also a constant. Okay, so let us see that. So here is what I have told here, right? So this first line is having number of operations, so two primitive operations 2, and I equal to 1, that is this one, right? This is happening only for one time, so there is no frequency associated with this, and it is there is only one primitive operation, that is assignment, so you have 1. Then you have I less than n, so it will happen for n minus 1 times the condition will be true and you will be entering the loop, and one last time, so which tells you that the condition is false, so you will be exiting out, right? So that is why this is 2n, and I equal to I plus 1, that is two primitive operation, one addition and one assignment, and that is executed for n minus 1 times. So the total time complexity taken here is 1 plus, that is this is for initialization, 2n is for condition checking, and 2n minus 1 is for updation. Okay, loop variable updation. Now this is for at the this will be checking for all the elements in the array except for the first element. So if the size of the array is n, then this is going to check for all the element in the array to declare or to announce that some element is maximum, right? So this will be executed for all the remaining elements except for a of 0. So n minus 1 times this will be done, and this 2 is because you have an indexing operator and a comparison, so which is 2 primitive operation count. So 2 into n minus 1. So n minus 1 is a frequency count for this statement. Now this, okay, so this will be happening only if this decision making statement is true, right? But we are trying to find an worst case time complexity. Okay, so worst case in the sense maximum time. Okay, so upper bound, so worst case in the sense maximum how much time I have to invest to get the result. Okay, so you can assume that the maximum element is at the end of the array. So till then I have to always this statement will be executed. Okay, so or it is say for example reversely sorted array. If the input is reversely sorted array, what happens? So you have say 10, then you have 9, 8. So what happens? This will be not execute. This statement will be always false and it won't be executed, right? So here it won't be executed. If it is sorted array, ascending order array, what happens? Always this condition will be true and this will be executed, right? So we are assuming a worst case maximum time. What will be the maximum time? So and again it becomes 2 of n minus 1 and this will be 1. So when you add all this thing, you will be getting 8n minus 2. So that is the time complexity of your algorithm, where n is the size of the input. Okay, hope this is clear. Okay, now growth rate of the running time. So we have to now measure the how fast your function or your function that you have found, that is 8n minus 2, is growing by the by the factor of n. So we represent this t of n as a function for measuring the time complexity. So you can see here in the array maximum element, to find the maximum element in an array algorithm. So the growth rate is linear. Okay, so in the sense once n is increasing, the time complexity for that is also going to increase, right? So algorithm array max grows proportionally with n. So that is a growth rate we call, right? So you are comparing the value of n with the speed at which you get the result. Okay, so that is called here as growth rate. So having said all those things, now we are going to define asymptotic notation, which will help you to find the relation of these various algorithms time complexity and decide which one is going to best. Okay, so one such time asymptotic notation is big O, right? So this is a definition of big O. So given function f of n and g of n, okay, assume that these are the two different time complexity or different algorithms f of n and g of n. We say that f of n is big O of g of n if there are positive constants c and n naught, such that this relation, this inequality is important, f of n is less than or equal to c into g of n for some n which is greater than or equal to n naught. Okay, so this is a definition. So you have two functions that you are comparing. Okay, if f of n is less than or equal to c into g of n, then I can tell f of n is big O of g of n. Okay, so here in this example you can see here three functions are compared: n, 2n plus 10 and 3n. Okay, you can see here n is having a linear slope, right? So you have, if it is 10, x-axis 10 and the output is also 10, right? So you have a linear growth here. 2n plus 10, you can see 2n plus 10 is also You can see this blue line 3n. So 3n, what happens in 3n? So these lines are not going to converge after some point, right? So it is going to parallel to each other. But you can see this point, right? This point where up to this point, this 3n was having a slower growth rate, right? Say if assume that this is 5, n is equal to 5 here, okay? So value of 5, it is 10, but for n is equal to 5, the value of this thing is somewhere close to say 20 or right. So what happens, this 3n is I mean 3n is not growing faster at this point, right? 2n plus 10 is having the upper bound, right? So at this point you can tell that 2n plus 10 is growing faster than 3n, right? But you can see here after this point when n is equal to 10, you can see 2n plus 10 is taking a different nature, which the growth rate is lower than 3n, right? And it goes parallel after that, right? So this point where you find a difference in behavior, it is taking an upper hand and it never converges. So this point is called as n naught. Okay, so that is n naught. Here you can see here n naught is equal to 10. Okay, so n naught equal to 10 and c is equal to 3. Okay, so how will you compute that? 2n plus 10 is big O of n. So you have to prove it. How can I tell that 2n plus 10? If I get some function as we did for array max, we got 8n minus 2, right? Similarly, for some algorithm you computed the your polynomial equation of finding the efficiency by counting primitives is given as 2n plus 10. Then how can you tell it is big O of n? Okay, so you have to substitute in this inequality f of n is less than or equal to c into g of n. So here 2n plus 10 and this is considered as g of n. So f of n is 2n plus 10, 2n plus 10 less than or equal to cn. When you simplify this, you can see here simplify, so cn minus you are bringing this right hand side to the left hand side to right hand side and inverting the inequality, right? So now you when you solve it for n, you will get 10 divided by c minus 2. Okay, so that is for what n which is having the upper hand. So when c value of c becomes 3, what is 3 minus 2? It is 10. So when all the values for all the values n greater than 10, 2n plus 10 is always less than 3n, right? So then I can tell f of n is big O of g of n. Okay, so hope this is clear. So this is how you will be proving your big O of n. Okay, please remember this equation, inequality f of n is less than or equal to c into g of n. Okay, another example here, another function is n square is not O of n. Okay, not big O of n. So n square is a quadratic equation, right? So you can see here when 10 this blue line is your n square plot, so 10 it is 100, right? So you can see here the value of n is linear, right? So definitely n square is having a faster growth rate than n, right? So this is having the relation. Now what happens, you can see 100n. So what is 100n here? So in the case of 100n, you can see here after this point again n square is taking the upper bound, right? So and for 10n, you can see here after say 10n, what happens? 10 into 10, 100. Again this is going to take upper hand. So for any constant value, I can find an contradicting c value, so that this is not at all an upper bound. So I can't tell that n square is not O. I mean, I can't tell that n square is big O of n. Okay, so this c should be constant, but here you can see in when you solve this inequality, c you are telling it c greater I mean n should be greater than or equal to c, or I can tell c is I mean n is less than or equal to c. So I can, this n is a variable, right? So I can find any n value which violates this condition inequality. So this n square is not big O of n. Okay. Another simplified analysis is eliminate all the lower order terms, right? So you will be eliminating because this is going to take an upper hand, right? So whatever be the worst case, the more time is spent on this 4n. So I need not consider all any lower order terms when I go for a big O notation, right? It's a worst case. So 4n, okay? Then 0.5 n log n minus 2n plus 7. So what happens? These all terms becomes a lower order terms, and 0.5 in log n is the maximum time consuming process, right? So then 2 power n plus n cube plus 3n, and 2 power n is having the faster growth rate, right? So this you can so that is how you will find. And now eliminate constant coefficients also. Okay, so here you can do 4n, means I will give n 0.5 n log n, then you will get n log n. Okay, so you remove the coefficients also, and so these are the when you get a polynomial you will find the dominating term. Okay, so and you remove all the lower order terms. Then if the dominating term is having some coefficient, you will ignore that coefficient also, and that will be the time complexity for the algorithm that you are considering. Okay, so big O and growth rate. So this is what we were discussing. So when can you tell that f of n is big O of n? Okay, so I was telling big O notation gives us an upper bound on the growth rate of a function, right? So you are finding an upper bound for the growth. Okay, so the statement f of n is big O of g of n, it means the growth rate of f of n is no more than the growth rate of g of n. So remember the inequality, f of n is less than or equal to c into g of n, where c is a constant. Okay, so now we can use the big O notation to rank functions according to their growth rate. Okay, so are the statement, I mean, is a statement here f of n is big O of g of n and g of n is big O of f of n, are they same? Okay, no, it is not the same. So you can see here, if this is a case 1 is g of n grows more. Okay, so what does that means? The growth rate of g of n is more. So if it is g of n is more, then f of n less than or equal to c into g of n is satisfied for this. So I can tell f of n is big O of g of n, but I cannot tell g of n is big O of f of n. Okay, now the reverse, f of n grows more. So the growth rate of f of n is faster than g of n. So will this equation f of n less than or equal to c into g of n will be valid? No, it will be valid only if g of n. So g of n is less than or equal to c into f of n in this case. So that is why this inequality. So I can tell if f of n is growing more, then g of n is big O of f of n. So that is why these two statements are not same. Okay, so same growth means you can tell both. Okay, so some common names for the time complexity. So O of 1, okay, let it be 100 or 10 or whatever be the number, but if it is a constant, then we will be telling it as O of 1, big O of 1. So when in logarithmic time complexity algorithms are there, so you will call that as big O of log n. Linear, that is O of n. Then you have log linear, O of n log n. This is super linear. Okay, so O of n power 1 plus c, where c is a constant. Then you have quadratic equation, right? So which comes a dominating term is n square. Then you have any polynomial, okay, n power k. So we call that polynomial. Then exponential, okay, so any constant power n. Okay, so these are the common names that we'll be using when you tell the complexity of any function. So we'll tell say the time complexity of finding a maximum element in an array is linear. Okay, so that's a it's a and that's why this names. So just note that. Complexity analysis. So how will you do the complexity analysis? So any primitive operations, we tell that as a constant time. So if you have consecutive statements, as we did for maximum finding a maximum element, so each line we counted the primitive operations, right? So if it is a consecutive statements, then you will be writing the sum of all the times. Then conditional. So conditional means all the branch. If true, so you will have a true block and the false block, right? So you will be finding the time complexity of true and false blocks, and whichever is having the maximum time taken, whether it is a true block or whether it is a false block. Based on that, the worst case time complexity is computed. Loops, you will be finding a number of iterations, how many times this loop is executed. Then you will have function calls. So if you have, say for example, a program, inside a program you are calling some other function, so the time complexity of that function will also be added to the time complexity of this in the calling environment. Okay, so function call means the cost of the function body is added to the calling part. Recursive function, so you will be framing a recurrence relation and solving the recurrence relation to find the time complexity. So which is not scope of this course 19 CSE 212 now. Yeah, so thank you.